All right, so we previously discussed the Sudoku principle, and we went through and proved it. Sudoku principle says that for any group, when you write out its multiplication table, or more precisely, its Cayley table, um, and when you write out the elements here and the elements here, and look at all the products that are formed by our group, what we find is that every row contains every single one of our elements exactly once, and every column does the same thing. So that's what our Sudoku principle was. Now what we're going to do is we're going to prove Lagrange's theorem using just the Sudoku principle, as well as the group axioms. So first of all, let's say what Lagrange's theorem is. Now, Lagrange's theorem has to do with subgroups, which I haven't actually described yet. But it's a pretty simple concept. You have some group G with some binary operation. Then H is a subgroup of G, which we'll write like this, exactly in the case that H, the set of H, is a subset of G. That doesn't have to be a proper subset. It could be G itself. But yeah, it's a subset of G. And H is itself a group. So in other words, we can say H is, I'm sorry, that should have had a line there as well. H is a subset of G, and H forms a group with the same operation as the operation that G forms a group under. Okay, so we say that H is a subgroup of G if H is a subset of G and H forms a group under the same operation. Okay, so that's what a subgroup is. Now, Lagrange's theorem gives us a really powerful constraint on the possible sizes of subgroups for any given group. So let's say exactly what it says. Lagrange's theorem. What it tells us is that for any H, which is a subgroup of a finite group G, if we have H that's a subgroup of G, which is finite, then the size of H, which we'll write like this, must divide the size of G. In other words, the size of G, the number of elements in G, is divisible by the number of elements in H. Another way to write this would be that there exists some number, some integer n, such that n times the size of H equals the size of G. This is equivalent to this. So, what this says, this is pretty strong. I mean, for example, let's say that we have a group of prime order, no matter what prime number that is. Let's say size of G is, let's say it's 7. What this tells us is that, maybe this group doesn't have any subgroups. If it does have subgroups, then those subgroups must have a size of something which divides 7. Well, 7's a prime number, so the only thing that divides 7 are 1 and 7. So the only possible sizes of subgroups of G are 1 and 7. Well, what's the subgroup of size of 1? There's only one such subgroup, and it's just the trivial identity group. All right, so the identity group is itself a group. We can prove that very quickly. Just look at the Cayley table. Clearly it's closed, it's associative, it has identity, and it has inverse Z, it's its own inverse. So this is a group, it's a trivial group. Every group has the identity group as a subgroup. And the other group is obviously just G itself. There's no other subgroup of G that has size 7. The only thing that has all 7 elements is G itself. So what we're saying here is basically, every group has at least 2 subgroups, the identity group and the full group. And the interesting thing is if there's any non-trivial subgroups, but Lagrange's theorem right away tells us that if the size of a group is prime, then it has no non-trivial subgroups. Okay? So that's going to be really powerful, and we're going to be able to get a lot of mileage out of Lagrange's theorem. So let me just circle this, and now let's go ahead and try to prove this. So move this over a little bit. Okay, so first of all, there's 3 cases. The first case So we have H, which is some subgroup of G. The first case is that H is one of our trivial, or the first two cases are that H is one of our trivial subgroups. So H is just this guy, the identity group, or H is just the group itself. Now, in each of these cases, Lagrange's theorem kind of follows trivially. If the size of H is 1, then clearly 1 divides any number, so no matter what the size of G is, it will divide it. If the size of H, if H is G, then the size of H is the size of G, and the size of G does divide the size of G because any number divides itself. So kind of trivially proven for the first two cases. Now the interesting case would be some non-trivial subgroup. So I guess we can just say, so we'll write it like this: H is a subgroup of G, which means H does not equal G, and H does not equal just the identity element. So we want to prove it really, we've already proved it for these first two. The interesting case here is here. We want to prove it for this one. So let's, first of all, think about just writing out the Cayley table for G. So we have some group. In general, we can have, we'll write its operation as multiplication as always. And now we can just start writing out the elements of G. Well, we don't know what the elements of G are, but we can give them names. And the nice thing, the thing that will turn out to be really useful about Cayley tables is that we can kind of choose whatever order we want to write the elements out that is convenient for us. And we're going to really use that fact in this proof. As long as we cover every single element of G, and as long as we get all these, get all these entries right, then we're fine. Everything's fine. So what we're going to do, in fact, is we're going to start with H. So H is a subset of G, so every element of H is an element in G. So, in fact, we can just start writing out elements of H. We can write them all out. Now, G is a finite group, which means H has a finite number of elements. H is a group, which means one of those elements is the identity. So we're actually going to start out with the identity element. Then we are going to have some other number of elements. We don't really know how many. We're guaranteed that we have at least one more element. We can call it H1. We're guaranteed that because we're assuming that H is not this trivial group. And, we can just continue H1, H2, all the way up to some HM for some M, where this, kind of covers the whole set H. And we can write it again on the column, E, H1, etc., down to HM. I'm actually going to block this off and just draw a little square around it. Because, so first of all, we know this is not all the elements of G, because we've assumed that H is not equal to G. So there's at least one more element out here which is not in H. So there still are more things out there. But we know since H is a group that it's closed, which means that everything in here is just other H, other HKs, right? So everything in here is an element of H. Everything in this block. And in fact, by the Sudoku principle, each row will end up covering every single element of H because you can't have duplicates. So every row exhausts all the elements of H, and so does every column. So, okay, that's our first thing. The next thing is that, like we said, there has to be some other element of G out here. And we can just call it G1. Right? We know that there exists at least one more element in our group that's not in our subgroup, so we call it G1. Now, let's just start filling out its table. And I'm not going to write the G1 down here. We could do it, but it's not actually going to be important for the proof. So first of all, E times G1, what's that? Well, that's just G1. Okay. Now, what is H1 times G1? Let's write it in here. Well, we really are faced with a question at this point. Is H1 times G1 something we've already seen? In which case we'd have to, give it the name of whatever that thing is. Or is it something new? In which case we'd have to give it its own column. So could it possibly be something we've already seen? Well, it can't be any of the elements of H. Because if it was an element of H, then it would have already appeared somewhere in this row. And by the Sudoku principle, we know that we can't have duplicates, so that's got to be a duplicate. So it's not one of these guys. Can it be G1? Well, no, because G1 already appears in this column. So what that tells us is that actually H1, G1 is its own new element, which is a little interesting because that tells us that it can't just be the case that you have one other element besides H. Like you can't have a subgroup which is the whole group minus just one element. If you have one more element, you have at least two elements. And in fact, we can continue this for h2 times g2. The exact same line of reasoning would apply. All the h's are blocked out, and now g1 and h1, are both blocked out as well by the Sudoku principle. So again, h2, g2 would be a new element, etc., all the way down to hm, gn. So what this is saying, I'll write this out here, is that you can't just have one or two or any random number of elements that aren't in H but are still in G. They have to come in this particular way, where for every element outside the set, it corresponds to one of the elements inside H. So the size of this is exactly equal to the size of H. Why? Well, because we had one of these guys for each of these. Right? This is E times G1. This one is H1 times G1, H2 times G1, etc., up to HM times G1. Right? So now, okay, so let's block this off as well. We'll have the same sort of feature as before, where each of these columns is going to contain every one of these HK times G1s. Why? Well, because, if we look at HN times HM times G1, right? Well, this thing is just HN times HM first times G1. So if we're looking at, this guy over here, basically what we're looking at is the equivalent thing over here times G1. Okay? So, basically, again, just applying the Sudoku principle, what we'll find is that this will cover all the elements G1 through HM G1. Each row will cover that. Now, okay, so maybe we're done at this point. Maybe we've already kind of covered all of the elements of our group, at which point we stop, and then we can conclude that the size of G equals 2 times the size of H, right? Because if we're done, there's no more elements of G, then we have all the elements of H plus another set which has the same size as the elements of H. But if we're not done, then we just continue. We pull out another element, G2. G2, well, let's fill out its table. We have E times G2, which is G2. Now we have H1 times G2. And then again, we ask the same question. Can H1 times G2 be something that we've seen before? Well, it can't be an element of H because this whole row is filled out. It can't be an element of these guys because each of these appears exactly once in this row, and that would mean there is a duplicate, and it can't be G2. So by the exact same sort of reasoning, we arrive at the conclusion that H1, G2 is a new thing. And similarly, we go through and we find, again, we have some set that ends with HM, G2 of size H of new elements. And now maybe we're done at this point. If not, we just keep going. And at some point, we have reached the end of our group. Why? Well, because G is a finite group, right? So G is a finite group, so we can't just go on with this forever. So at some point, we'll say we get to some final element, which we'll say is Gn. And then when we add on Gn, again, we are logically forced to, to conclude that there must exist something H1Gn, and there must exist H2Gn, all the way up to HMGn, by the exact same sort of reasoning. And that will lead us to ending up with n blocks of size H that totally cover up and partition our group. And that'll tell us that G equals n times H. And that's the proof. That's what Lagrange's theorem says. So the basic idea of this is that if H is a subgroup of G, then you can form blocks of size H that cover the whole group, that cover all of G. And the reason you can do this is because if H is a subgroup of G, then every time you add in one more element, you're forced by the Sudoku principle to actually add in m plus 1 new elements. So you have to add in one new element for every single element of H. And that happens every time you try to add in just one more element. You can't just add them in one at a time. You have to add them in m plus 1 times at a time, the size of H times at a time. And there we go. That's Lagrange's theorem.